Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on MATLAB simulation of control systems. Today we are going to discuss the sliding mode control, which is the anti-disturbance sliding mode control for permanent magnet synchronous motor speed regulation. So this is a paper published in IEEE Transactions on Power Electronics in 2020, and let us see what this paper discusses about. So this paper presents a new sliding mode reaching law, which the authors are claiming that the power term is bounded by the absolute value of the switching function, and it effectively suppress the inherent chattering in the sliding mode control. And then they have also proposed the anti-disturbance sliding mode speed controller, and they present some simulation results to show the performance of their proposed controller. Here is the introduction section, which we are going to skip for our purposes. I am sure it presents some nice background of the problem and all the motivations related to the problem. And here is a list of contributions by the paper. They have proposed a new sliding mode reaching law. Then they have the observer. They have proposed the hyperbolic tangent function based observer for the disturbances, and anti-disturbance sliding mode speed controller is designed in this paper. Okay, so section 2 presents their sliding mode reaching law design and analysis. Reaching law that they have proposed is basically, so I'm not going to go into the basics of sliding mode control because I have already made quite a few videos about sliding mode control in my channel, and you can go back to those videos which explain the basics about the sliding mode control and how the sliding surface is selected, and what is the role of the derivative of the sliding surface. We are going to go down to the business straight away in this video. So here their proposed sliding surface is I think this is the derivative of the sliding surface, ds by dt, which is minus epsilon times the absolute value of the state variables raised to the power a times sine of the sliding surface. So sliding surface should be somewhere around here. Where is it? Okay. Oh, there is the sliding surface. S is equal to E dot plus CE. E is basically the error, which is the difference between the desired angle of the motor and the actual angle of the motor, which you can call like the position of the motor, and and the E dot is basically the derivative of this error. So this is the sliding surface, and then there is the derivative of the sliding surface, which has all sort of exponents involved in it. So this is the derivative of the sliding surface presented in the nonlinear form. This is what we are really interested in, equation 10. That is the main thing for us, because this is the control law that results from the sliding surface and its derivative. And here are some values of the parameters used in the simulations. The initial condition, initially they have just this model, j theta double dot is equal to u plus d, where j is the rotary inertia, theta is the position, u is the control input, and d represents the external disturbance. So they have selected f of theta t is 25 times theta, which is a linear function. H is equal to 133. It's just a constant coefficient. And d of t, the disturbance, is set as 10 times sine of pi t. So sinusoidal disturbance. And well, if you go to the MATLAB, I've already written the code for it in order to save some time. So this is not a large no, it's a very simple and short MATLAB code. So here are some values of if I put it side by side. So these are the values of some coefficients. So C is equal to 15, E epsilon is equal to 10, K is equal to 20, A is equal to 0.5, B is equal to 0.3. So here A is equal to 0.5, B is equal to 0.3, C is equal to 15, epsilon is represented in my code by E, K is equal to 20. This is the so th is the desirable value of theta, which is theta d. They have mentioned it somewhere around here. Yes, so theta d is set as sine of t. So this theta d in the paper, which is sine of t, this is th in my code. And of course the derivative of sine t is cos t. So the derivative of theta d is cos t, which is right here. And we also are going to use the double derivative of theta, because you can see here in this expression for the control, there theta, double derivative of the theta is appearing, and double derivative of theta dot actually does not appear. So we will have to look into this. Okay. Okay, so probably there is a typo in the paper, because I really expect here that this theta double dot of the desirable value of the theta should be here, because the control itself is appearing in the theta double dot, so it should not be depending upon the theta double dot technically. So anyways, in my code I have used the desirable the derivative of the desirable value of theta. So I have instead of the theta double dot, the double derivative of the actual value of theta, I have used the theta the double derivative of the desirable value of theta in the control equation. So here S is equal to theta, so it is if you look into this equation for S, go above. So S is equal to E dot plus C times E. So E dot is the derivative of the desirable value of theta minus the second state variable. So I have two states in the system, x1 is theta and x2 is theta dot. So the derivative of the desirable value of theta, which is cos of t, minus the value of theta dot from the state equation, plus C times E, which means that C times the desirable value of theta minus the first state, which is the theta itself. And in the control I have 1 over let me see, is it 1 over h. So what is the value of h again? Here the value of h is 133. So it should really be 133. So it should be 1 over 133, because here h is 1 over 133. So if you go back to the control equation, we have u is equal to 1 over h times so 1 over h means 1 over 133 times e times the norm of x raised to the power a sine of s plus k times absolute value of the sliding surface raised to the power b times sine of absolute value of s minus 1 times s plus c times theta dot, the derivative of the error, and plus here I have used the double derivative of theta desire. So here I am assuming that there is a typo in the paper, and f of theta t is given as 25 times theta. So then d is 10 times pi t, which is given here. If you go down here, so this is 10 times pi t, this is the value of d, and the equations, of course, theta dot is equal to the derivative of the first derivative of the theta is equal to theta dot, and the derivative of the theta dot is equal to minus this here, minus f of theta t, which is 25 times theta plus 133 times u plus d. So that is all. So this is our state equations, and here is the code which calls the ODE 45 function for these state equations for 15 seconds. The initial conditions -2 and -2, these are given in the paper. So if you look at here, the initial condition is -2 and -2, and you can then calculate the control input here and plot it. So if you run this file and we wait for it to compile, let's see how it's doing. It's still busy. It's a little bit complicated process. So meanwhile we can go back to the paper here. Okay, the results are here. So this is the simulation of the control, and this is the simulation of the reference signal is in blue, and you can see that the actual value of theta is it's covering the reference signal entirely, because the reference tracking is almost perfect. And if you go into the paper has shown the results. I believe these are the I think these are the results, the equation A2 and B2. Let me see. So A is for TERL. We have used the NS new sliding mode reaching law, which is A2. So A2 and B2, so that is where we should be looking. So A2 and B2. So if you look at A2 and B2, this is the figure in the paper, and this is our result. It's quite similar. And if you go to the other figure 2, this is the control law, which is a little bit different. I don't know why their control law is going up to 120 and coming back to nearly 0. Our control law here is doing almost the same thing, but it is not going up to 120. It's just going up until 60 and coming back. The behavior is quite similar, but not exactly the same. So I mean, it could be the issue could be that we have the only difference between this paper and my code is that I somehow am not convinced that this is theta double dot. I really think that this is theta double dot desired. So that's the only difference I can tell. So anyways, overall this is how you would simulate this permanent magnet synchronous machine second order model. And the next is a little bit of the detailed discussion. So for example, if you go to section 3, so section 3 is the design of anti-disturbance sliding mode speed control based on the new sliding mode reaching law. And in this section they have given the detailed model of the motor. For example, the DQ rotating coordinate system current differential equations. So I have already written the code for this detailed model as well. So let me go to that. So this is the model. So in my model there is some, you know, there's some constants which I will walk you through as I go along in the paper. So first of all, these differential equations, d by dt of id, which is the d component of the current, and d by dt of iq, these are the first two equations here in my code, which is x1 dot is basically d by dt of id, which is equal to ud minus r times id. Id is the first state variable in my code, minus ed divided by l, and x2 dot is uq minus riq. IQ is state x2 in my model, minus EQ divided by L. So these are these two lines in my code are equation 19. Of course, the value of L is given. Actually, the value of L is not given in the paper. I have assumed it to be 5 millihenry. I was unable to find the value of L in the paper. So if you are able to find the value of L in this paper, please go ahead and plug in the correct value. So and then the value of stator resistance is actually given in the paper, so I have used it to be 1.55. this is straight from the paper, table number 1 of the paper. The equations of ED and EQ are also given in the paper. Here are the equations of ED and EQ. So if you look at I think I have so these are the equations of ED and EQ. So ED is equal to minus omega E times LQ times IQ. So minus omega E is defined here, number of poles times the mechanical frequency omega R. Omega R is state number 4 here. This is omega E is equal to number of poles in omega R. Again, I could not find the number of poles in the paper, so I assumed there are 6 poles in the motor. So if you are able to find the correct number of poles, you can plug it in the code. And then you have this so minus omega E LQ. The value of LQ is given in the paper, so I have used this value. LQ is given to be 6.71 millihenry, so that would be 6.71 e to e minus 3 in MATLAB. And similarly, value of LD is also given. So ED is omega E times LD ID plus phi f. So phi f in my code is 0.175. The value of phi f is also not the value of psi f is also not given in the paper, but there is a value of psi a. So I have used the value of psi a for psi f, which I am not sure whether, I mean, it definitely it's not the correct way, but you know, for the sake of you know, for the sake of demonstration, it serves the purpose. Then you have ED is ED and EQ. The equation of EQ is written here, omega E times LD, and x1 is of course ID is our first state, the D component of the DQ current, and phi f we have used this constant value. Omega E is equal to P times omega R. Again, P, the value of P I have assumed to be 6. Then there is this equation. This is the mechanical motion equation of the motor, which they have simplified to this value here, omega r dot. So of course theta dot is equal to omega r, so x3 dot is equal to x4. X3 is the rotational angle in our code, and x3 dot is equal to x4 simply means that theta dot is equal to omega, and omega dot is equal to x times the desirable value of iq, which is this iq, this x is capital X in my code. Okay, so capital X, as they have mentioned, this is 3 times p square psi f divided by 2j. The value of j is given in the paper. I have used it from the paper. And PF, I have already told you that psi f is not given, but psi a is given in the paper. Number of poles is not given in the paper. Actually, this x is 3np square. Well, np can be, n could be a rotational speed, or it could be number of poles. There I could not find any explanation about what np is, so I just use the number of poles in here. You can do as many, you can, if you can contact the authors and ask them about what np is, and then you can plug in the value that you deem fitting. Then there is this so g is equal to not this g, but we are here in omega r. So x4 dot is capital X times the script x times iq star plus g plus d. So here g and d are also the state variables, because g and d are dynamic. They are measure of uncertainties and disturbance torque. They actually later on vary this load torque and see if the variation of the load torque affects the rotation speed or not, and how it affects. So here we have x4 dot is equal to x times x2d. x2d in my code is this iq star, plus x8 is basically this g, and x6, that is basically this d. So d is x6 in the code and g is x8. Then x5 dot is basically this the dynamics of the ESO, this hyperbolic tangent function based sort of observer. So here z1 dot is equal to z2 plus g plus x times this and this. So this is encapsulated here. So z1 is x5 and z2 is x6. So z1 dot is equal to z2, which means x6, and plus g remember is the x8, so in our code. And this is capital X, and x2d is iq star minus beta 1. Beta 1 value is given in the paper, and e1 is defined here in the code. So e1 is x5 minus x4, which means that it is z1 minus omega r. Omega r, the rotational frequency speed of the motor, that is state variable number 4 in our paper, and z1 is state variable number 5. Then there is z2 dot, which is minus beta 2 tangent hyperbolic beta 3 times e1. It is written here. x6 dot is equal to minus b2 tangent hyperbolic b3 times e1. And then we have to add certain more state variables. Why? Because when they use the sliding surface, so sliding surface has the integral of error. Wherever there is integral involved, you have to define a new state. So if the integral of error has to be in the sliding surface, then I have to define a state x7. The derivative of x7 is equal to error. So this is error. This is omega r desired value minus x4. x4 is actual value of omega r. So desired minus actual value of omega r is the error. And if x7 dot is equal to error, then x7, the seventh state variable, will be the integral of error. So that is the logic of integral control. I also have a video explaining how to implement the state space based integral control in MATLAB. That is a quite simple one. You can watch that if you do not already know how to implement integration in the state space format. Then x8 dot, that is basically x8 is our variable g hat, because g is the representation of uncertainties, so the estimation of g comes from g dot is equal to minus eta s. So this is our 8th state variable. Then 9th state variable is simply so 9th and 10th state variable come from the fact that there are going to be two PI controllers. So here if you look at so they have implemented this in Simulink. I am not really a very big fan of Simulink, so I have not implemented this in Simulink, although you can just use this same kind of, they have given away how you can implement this all of this stuff in Simulink, so it is very clear. I think if you know how to use Simulink, you can easily do that. At the end of this video, I will also show you how you can get the permanent magnet synchronous machine in the Simulink. So Simulink already have let me just spoil the fun and just give you this. So this is the feedback control of a permanent magnet synchronous machine, and I did not build this Simulink model. This is given in MATLAB. So if you want to get a hold of this model, all you have to do is type this command. So type this command in your MATLAB browser, and your MATLAB will automatically open the Simulink model of the permanent magnet synchronous machine. So the command is power underscore PM motor, power underscore PM motor. So if you enter this command in just the command window, the Simulink will open up this built-in code, built-in model. You can copy this model and paste it into a new file, and then you can make edits into this model. Like you can add, so here there is only one PI controller. You can add the second PI controller. You can add the two blocks here, which are basically equation 32 and equation 28 in the paper. We have implemented equation 32 and 28 in here in our script code. So we don't need to do that on Simulink as well. But Simulink has its own advantages. I mean, there is a DC power. We don't use DC power in the script code, and there might be certain things that you can do in Simulink and maybe you can not do in the script files. But anyways, back to our script file. So the x9 and x10 are the integral states that are developed for these two PI controllers. So if you look at these PI controllers, actually UQ and UD are the, if you look at here, this is UD and UQ. So UD is equal to proportional gain times the state x1 and integral gain times state 9. State 9 is basically the integral of the error. The reference value for id is equal to 0. So the error is 0 minus id, which is just minus id. So my x9 dot is minus x1. That means that the state x9 is integral of the error 0 minus x1. Then UQ is equal to KP times the desirable value of IQ and minus the actual value of IQ, which is x2, and plus KI times x10. x10 is basically the integral of the error between desirable and actual value of IQ. So this is these are the 10 state variables that you have to use in order to fully encompass the model that is given in this paper. So this is the model starting from I don't know, equation number 19 and all the way up to, you know, these equations. I have skipped the equations that are not relevant to the model, so this up all the way up to equation 33. So for example, we don't need the intermediate equations. For example, we don't need this equation. I suppose E dot does not appear in here. So we do need the equation of E. All right, so this is if you look at it from the start, omega desired, you can set it to any value, any constant value. So derivative of omega desired will all of course be 0 if omega desired is a constant value. And then this is number of poles. The A value is given in the paper, B is equal to 0.3, C 20. It's all given in the paper. So these values have been taken from the paper. Omega E is equal to P times omega R. Omega R is the fourth state variable. Value of the this inductance is not given, but I have assumed to be 5 millihenry. These values are given in the paper. The value of the resistance is from the paper. This value is again assumed. These two values are given in the paper, and then so on. So this is ED, EQ, E1, eta. Then the sliding surface is omega desired minus omega plus C times x7, which is the integral of the error between the omega desired and omega. So if you look at x7, this is the derivative of x7 is equal to error, so which means that x7 is the integral. This is the main you can say the equation of the control, because the desirable value of IQ is sort of like the whole controlling part. So this is 1 over, so if you go into the paper, it's given right here, equation number 32. So if you go here, this also says that equation number 32 has to come into the Simulink file. So equation number 32 is this one. So this is 1 over, if you compare side by side, this is alright. So this is 1 over x omega r dot minus g hat. So this is omega r dot minus g hat is state number x8 minus d is state number x6 times eta and norm of the state. So I have taken the state to be just you know, x4 omega r, and the sign of the sliding surface, and then you can go like this whole equation is the same as this C times error. Error is desirable value of omega minus the actual value of omega. So this is the whole code. You can just copy this, you know, by taking the screenshot, and then let's go to its implementation. So it's in implementations, I just used all 0 initial conditions, and remember that we have given the desirable angular velocity to be 3000, and I have just I can plot the state variable number 4, which is the velocity. So if I run this code, so what happens is that, so I'm running it for just 1 second. So you can see that velocity goes from 0 to all the way up to 3000, and it's also almost perfectly tracking. We can just zoom to see if there are any problems. There seem to be some fluctuation, but it's I think it's a negligible. There is some fluctuations in the velocity, but I think the magnitude of fluctuations is quite small. But anyways, we can change the desirable value, from 3000 to, let's suppose, 1000, and save it and go to the script file, run it, and this goes to now 1000. Similarly, you can go to any constant, let's say 700, save it and go to, like, this is 700. So I mean, I have tested quite a few constant velocities. If you look into their file, so they have like the velocity goes up and it settles to whatever desirable value they want to achieve. Here they want to achieve like 1000 rpm. So, and these are the values of the currents. So you can also plot values of the currents here. So for example, let's plot the state x1. So this is the value of the current. If you look into that, so this is the current initially, large fluctuations, and then it basically it goes like this. So this is the value of the first state, which I think it's id. This is the value of id, and we can also plot the value of iq. So if you, so we can go into the value of iq. So the value of iq is the second state variable. So we can run this, and this is the value of iq. So you can see here some large fluctuations initially and then smaller fluctuations later on, and like overall it almost settles to, what value is this, okay, minus 2.383. so it's fluctuating around about minus 2.383. and similarly you can go for the angle. So it goes from 0 to 700 radians. So I don't know how many revolutions that is, but we have set I think 700 rps is our rpm. So this is our desired velocity. So you can calculate how many revolutions it should be doing in 1 minute, and 700 radians, and how many, so 2 pi radians is 1 revolution. It's about 6 radians, so it's doing about, I don't know, 100 revolutions or something in 1 second. Okay, then we have 10 state variables. These first four state variables really are the ones that matter the most, and the other state variables are either integrator states or some other states that are used in the calculations for like, for example, the state number 5 and 6. These are for observing the disturbance torque and etc. And then the state number 7, 9 and 10 are integrator states. State number 8 is the dynamics of your uncertainties. So this is basically the simulation of permanent magnet synchronous motor. I hope that this video was useful for you to learn how to simulate permanent magnet synchronous motor, or especially how to simulate sliding mode control for permanent magnet synchronous motor. Well, still you can use the Simulink model in the MATLAB. I have this is built in to the MATLAB. If you like, for example, run it, So it shows you the but here this is, of course, you will have to add a PI controller here, and you will have to add the equations of equation 32 and equation 28. 2 or 3 blocks you will have to add into this built-in simulation file, and then you are good to go. So in order to summarize, we have first of all, we have simulated a simple model, two-state model for the motor, and we have seen how it tracks the sinusoidal desirable velocity and desirable angle, sorry, not velocity. The sinusoidal desirable angle, which basically translates into some constant velocity. And then we have used the detailed model of the permanent magnet synchronous motor described in the paper. Some of the coefficients, some of the values are not the same as that in the paper. Some of the values I could not find in the paper, so that you have to keep in mind. But otherwise, I mean, this is it. This is how you do it. And again, this is the in order, so I think this is the simulation is done, so we can look at some results. So these are the results, these are the currents, large fluctuations in the beginning and then the small fluctuations later on. But this is not this is ABC currents. These are ABC currents that what we saw was the DQ component current. So there is a DQ to ABC and ABC to DQ transformations as well, which just converting from one frame to another. This is the speed, so you can see that within almost within one, what is this, 10 millisecond, yeah. So within 10 millisecond it is going to the desirable speed. You can give here, so this is 700 reference. You can change the reference to any other value and run it again. But this is the built-in MATLAB controller for permanent magnet synchronous motor. I did not modify it, I just copy it. You can copy it too, and you can if you are really into reproducing the same simulating file, you can just add these 2 blocks or these 3 blocks, the PI block here and the 2 blocks of this and this. You can add to that model and get the same simulating file as in the paper. So that is it. And next time we'll come with another research paper, and stay tuned. And if you want to get notifications, please do subscribe and hit the bell icon. And thank you very much for listening once again. That's all.